Okay, last little section to consider, I suppose, here is the amortization formula. Very, very closely related to the last section that we just looked at. Okay, so very, very closely related here. What we're looking at here is we're looking at monthly repayments, generally for a loan or a mortgage or something like that, and calculating the value of those repayments that are to be made. And we saw that in a few of the examples or a few of the questions there, where that was the goal, was to calculate how much would I have to repay in order to have that amount, or how much would I have to invest to have that amount after a certain length of time. And those really are the two uses of this formula. And what it calculates is it calculates the repayment, which we call A, of a principal for a principal amount P at a certain interest rate for a certain number of payments or compounding periods. And this formula can only be used where the payments are made at the end of each period. We'll see why that is in terms of the derivation here. I'm just going to kind of talk us through the actual example of the derivation here as opposed to writing it out. So when we're deriving this formula, and this is something that we should know, okay, it is I suppose a learned proof or a learned derivation here. So if we let the amount that was borrowed be P and the regular repayment be A, then the amount P borrowed is equal to the sum of the present value of each repayment. And that's very closely related to what we were looking at in the previous video. So if I'm making these repayments monthly, then the current amount that I have borrowed, that I'm going into the bank to borrow now, is the present value of all of those repayments that I'm going to make in the future. So if I'm going to pay $250 every month now for the next 20 years, the amount that I have borrowed needs to be equivalent in value. So I need to pull back all of those $250 payments to see what their value is now, and that should total the investment that I've made. So in terms of setting that up, we kind of set it up as followed. It's mainly looking at present values. So it's a sum of present values to set up a series where A is the repayment that I've made, and I'm pulling it back in terms of the length of time there, 1, 2, up as far as T for however many payments there are. This, of course, then is a geometric series where we have an initial term of a over 1 plus I, a ratio of 1 over 1 plus I, and an n of just t, so there's t payments, and of course we have our formula for the sum of the series. So we can identify or fill in all of that formula there. Okay, what largely follows here is a fair bit of algebra, I suppose. And the key thing to remember here is that what we've done with this overall sum is we're looking at calculating p. Like that sum will give me p, which is the amount that I borrowed. Okay, so that's the idea, is that if I repay all of this money, that it should be equivalent to the amount that I borrowed. So, however, what we're looking to derive is a formula for A. So our overall goal here is always to try and get A on its own. So we can see kind of where we get to a point here where we have P equal to A times 1 plus I to the power of T minus 1 over 1 times I plus 1 to the power of T. Okay, so we can kind of get to that sort of formula there. We, however, as we said, want A on our own. So instead of that, we are going to divide by this entire bracket here. And what that does is from here to here, we're basically just flipping the fraction. Okay, so you can kind of see it there. We're just flipping the fraction. That's all that division by a fraction is. We flip the second fraction and we multiply, and we end up with that formula. What I suppose is handy about a derivation or a proof like this is that you know the end goal. So hopefully if you can make it to that certain point in the middle, you kind of should be able to kind of lead yourself through then to the very, very end goal. So let's just look at using this formula very quickly. I'm not going to dwell upon it too much because really the two examples here I suppose cover maybe the two styles of question that we could be asked, and then in terms of exam questions you're tying it together really with some of those previous styles, so setting up the series, comparing the two, and I think this is a formula that a lot of people veer towards. If you're not directed to do the series, you could be directed to do it, so you should know both, but in the absence of any direction, you're kind of free to use whichever. And sometimes people like this one in terms of calculating the repayments or the overall value of the loan or mortgage. So here a loan of 375,000 is taken out at an interest rate of 5.6% per annum. How much should annual repayments be? If it's to be paid in 10 equal installments over 10 years, the first installment is paid a year after the loan is drawn down. So that idea that say is paid in like December. Okay, and December is when I kind of pay the first installment. I took it out in January. December time is kind of when I'm paying it. So we're going to be using our formula here, okay, which is provided for us in the formula and tables book. 1 plus I to the power of t over 1 plus I to the power of t minus 1. Let's fill in anything that we can here. The principal value is 375,000. My interest rate is 0.056, 1.056 to the power of 10, all over 1.056 to the power of 10 minus 1 gives me an annual repayment of 49989.32. So €49,989.32. A customer decides instead to make monthly repayments. So to make monthly repayments, we need to look at the interest rate. So 1.056 being equal to 1 plus m to the power of 12. This same sum I think that we've done multiple times now, 1.056 minus 1, and we can calculate that value here. 1.056 minus 1 is 0.004551. Okay, so setting it up in the same way again, the principal has not changed. The interest rate, of course, has changed because now it's compounded monthly, so we would be incorrect to use the same interest rate. Okay, it's 10 years, but we want to make monthly repayments for that same length of time, so 120. 1.004551 for 120 months minus 1, and that gives me €4,062.31 in terms of my repayments there. So slightly smaller repayments if I'm repaying monthly there as opposed to repaying yearly. But you can see how it didn't really change our approach to the function. If anything, the only thing we really had to adjust was the interest rate there in terms of using the function or the formula. You're just filling in kind of as normal here. Jack then wishes to have €500 per month for 4 years while at college. How much money do his parents need to invest at 5.2% per annum compounded monthly to provide the money that he needs? Okay, so let me see. He wants to have €500. He wants to have €500 at the end of, or he wants to have €500, excuse me, for the 4 years while he's at college. For 4 years, he wants to have repayments of €500. So how much do his parents need to invest overall to ensure that that fund remains? So what we're looking at here is that the principal is unknown, the repayments are known, the interest rate is 0.052 per annum. Okay, so we'll just say that's yearly, and the length of time is 4 years, but we were looking monthly, so that's 48 months. Let's focus on the interest rate here. I'm just going to jump a little bit to what we've been working at, I suppose. So that's 1.052 minus 1, which gives me a monthly interest rate of 0.004233 overall. So let's fill everything in here. A is equal to P times 0.004233, 1 minus, or not 1 minus, excuse me. I almost forgot this formula. 1 plus, so 1.004233 to the power of 48 over 1.004233 again to 48 minus 1. And the overall goal here, I suppose, is that we know what the monthly repayment is. We know the answer is 500. So through a little bit of reworking here, before we fill it into the calculator, all over 0.004233, 1 minus 0.0423348, gives me an overall principal value of 21677.52. So they would need to have €21,677.52 to be able to provide €500 per month for those 4 years. Okay, so hopefully we can get a sense there of kind of the application of that formula and also a sense of when to apply that formula. So we would apply that formula when we're looking for installments or regular payments that are made from a loan or a mortgage or a larger sum there. And we can also use it if we know the regular payment to work out the larger sum, with that stipulation that the payments should be made at the end of the month, because that's how the formula was derived, and kind of that we have that idea of where the formula comes from, so that the payments generally are made after or following the investment of a certain amount of money. And I suppose that if we've kind of all of that set up, then we're free to use the formula. And in the absence of that, maybe setting up a series can be more beneficial. Sometimes they'll look for you to compare the two. But there's a few exam questions there within that section that kind of get into that in a little bit more detail, that provide a little bit more clarity on that front.